Hey folks, I am back. It's now 12:32 a.m. night here. I'm here in my garage. But I wanted to, there was this 2024 United States Data Center Energy Usage Report. It's a 70-page document. I'm not going to read the whole thing, but I wanted to at least read the first part of it to give you a taste of what it is. I do think that it's a good read for anyone who's in the AI infrastructure space or the data center space. It's a good read, and it's good to know what their findings are. These findings were they took some information from 2014, etc. I think this was done in around 2020 and between 2024, but they took all that data, and then they also use the information that they found to kind of estimate what they think things would be by 2028. So this is a report that speaks to how things went from 2014 and where they think they're going to be in 2028 from an energy usage perspective. All right. So I set up. I'm not sure if you saw my last video stream. I had a couple that were tests. I started the streaming and I didn't even have audio going. So this is now everything is set up. I'm streaming to LinkedIn as well as to YouTube. All right. So anyway, I hope that you find this beneficial. I think it is. What I did is I downloaded the PDF, and so I'll be reading through the PDF as I go. All right, cool. Just want to make sure that I know it's streaming. So this is where we're going to do. We're going to look at the executive summary. We're going to kind of read through that part and then go from there. I believe I have it zoomed out enough to where you should be able to see or read along with me. There we go. And I just increased it just a little bit more, so that if you're following along, that you shouldn't have a problem. Yeah, perfect. All right. So let's get to it. So this is the executive summary. I'm gonna go through it right here. The Energy Act of 2020 calls for the U.S. Department of Energy to make available to the public an update to the Lawrence Berkeley National Laboratory's prior study entitled United States Data Center Energy Usage Report, and that was back in 2016. This report, designed to meet the congressional request, estimates historical data center electricity consumption back in 2014, relying on previous studies and historical shipment data. This report also provides a scenario range of future demand out to 2028 based on new trends and the most recent available data. Figure ES1, so this figure right here, I'm gonna make sure that come up on the screen. Hold on 1 second. I don't think that you're seeing this, so give me 1 second here. All right. So now you guys should be all right. Yep. So you should be able to see that. So this report, here we are, figure ES1, provides an estimate of U.S. data center electricity use, including servers, storage, network equipment and infrastructure from 2014 through 2028. And as you can see here, at this point, data center electricity was about 1.9%. I don't know why this is coming up. Okay, got it. And then here, this is actually 2023, this part right here. And this is now at 4.4%. I'm getting used to this, okay? So .4%. All right. Other figure ES1 shows U.S. data center annual energy use remained stable between 2014 and 2016 at about 60 terawatt hours, continuing a minimal growth trend observed since about 2010. In 2017, the overall server installed base started growing, and GPU accelerated servers for artificial intelligence became a significant enough portion of the data center server stock that the total data center electricity use began to increase again, such that by 2018, data centers consumed about 76 terawatt hours, representing 1.9% of the total U.S. annual electricity consumption. U.S. data center energy use has continued to grow at an increasing rate, reaching 176 terawatt hours by 2023, representing 4.4% of total U.S. electricity consumption. $176 kilo. Man, I can't use this thing. Anyway, 176 terawatt hours at this point here in 2023. The significant changes observed in the data center sector in the recent years, owing to the rapid emergence of AI hardware, total data center energy use after 2023 is presented as a range to reflect various scenarios. These scenarios capture ranges of future equipment shipments and operational practices, as well as variations in cooling energy use. The equipment variations are based on the assumed number of GPUs shipped each year, which depends on the future GPU demand and the ability of manufacturers to meet those demands. Average operational practices for GPU accelerated servers represent how much computational power and how often AI hardware in the installed base is used to meet AI workload demand. Cooling energy use variations are based on scenarios in cooling system selection type and efficiency of those cooling systems, such as shifting to liquid-based cooling or moving away from evaporative cooling. Together, the scenario variations provide a range of total data center energy estimates, with low and high end as of roughly 325 and 580 terawatt hours in 2028. So based on their estimates, right, looking at maybe how cooling might change, maybe thinking about the how much GPU servers are estimated to be in play at that time, and also even the efficiency on how those servers or the GPUs are implemented. They're saying the rough estimate, low end, 325 terawatt hours to 580 terawatt hours. This is in 2028, when they said in 2023 what was it, 176, right? So basically doubling by 2028. Assuming the average capacity utilization rate of 50%, this annual energy use range would translate to a total power demand for data centers between 74 and 132 gigawatts. That would be the data center power demand. This annual energy use also represents 6.7% to 12% of total US electricity consumption forecast for 2028. So data center consumption was 176 terawatt hours. They estimated that that was about 4.4% of total US energy use. And now they're estimating that that's going to move up, right, between 325 and 580 terawatt hours. And that's going to be about 6.7 to 12% of total US energy consumption. I think you guys might have missed some of this reading. So I'm here on the second page right now, and I'm going to go through. I'm going to keep my eye just to make sure that the PDF is scrolling on the stream as I'm reading. Historically, data center electricity use increased substantially from 2000 to 2005, roughly doubling during that period. During the early and mid 2010s, a shift from on-prem data centers to co-location or cloud facilities helped enable efficiency improvements that allowed data center electricity use to remain nearly constant at a time when the data center industry grew significantly. With a large expansion of data center services, the efficiency strategies that allowed the industry to avoid increased energy needs during this period included improved cooling and power management, increased server utilization rates, increased computational efficiencies, and reduced server idle power. While many of these efficiency strategies continue to provide significant energy efficiency improvements in data center design and operation, the expansion of data center services into areas that review new types of hardware has ended the era of generally flat data center energy use. Most notably, the rapid growth in accelerated servers has caused current total data center energy demand to more than double between 2017 and 2023, and continued growth in the use of accelerated servers for AI services could cause further substantial increase by the end of this decade. The current and possible near future surge in energy demand highlights the need for future research to understand the early stage, rapidly changing AI segment of the data center industry and identify new efficiency strategies to minimize the resource impacts of this growing and increasingly significant sector in our economy. Areas of future research identified in this report include benchmarking initiatives, collaborations with electric utilities, and technology development, all of which would be furthered by greater transparency in data center energy use, as the lack of data availability significantly limits the analysis in this report. The estimates in this report are based on a bottom-up energy use model that calculates total electricity use from an installed base of data center equipment. This method avoids overestimating that can be caused by tracking data center load for projects that have not yet selected a power provider. Where am I at here? pause a second, please. All right, so I'm going to read over this line right here. Make sure that you are in line. This method avoids overestimation that can be caused by tracking data center load for projects that have not yet selected a power provider, but requires many inputs and assumptions developed from limited publicly available data, proprietary market analysis data, and review by industry representatives and stakeholders. So bottom line, what they're saying is that they'd like more transparency, but from what they've done, they took it from what has been installed, not just what's estimated at this point. They started there first in order to get their information. The lack of direct energy data available in a sector with rapidly evolving technology limits the analysis in this report, especially when trying to understand and estimate future energy scenarios. The results presented here indicate that the electricity consumption of U.S. data centers is currently growing at an accelerated rate. The ES1 figure that we showed earlier, it shows a compound annual growth rate of approximately 7% from 2014 to 2018, increasing to 18% between 2018 and 2023, and then ranging from 13% to 27% between 2023 and 2028. This surge in data center electricity demand, however, should be understood in the context of the much larger electricity demand that is expected to occur over the next few decades from a combination of electric vehicle adoption, onshore manufacturing, hydrogen utilization, and the electrification of industry and buildings. So it's basically saying, hey, look, as I know we're talking about data center, but as data centers continue to expand and do their thing, we can't forget that there is also other industries as well, and therefore they're going to have an impact on the total usage. Research initiatives are needed not merely to identify strategies to meet data centers' future energy needs, but also to help stakeholders use this relatively near-term electricity demand for data centers as an opportunity to develop the leadership and strategic foundation for an economy-wide expansion of electricity infrastructure. So that was the executive summary. And this is for, again, the 2024 United States Data Center Energy Usage Report. I wonder if I have a little bit more time. Well, I really want to read through a little more. So what I'm going to do is I'm going to go ahead and read through the introduction and then go from here. In the United States, demand for computation has increased as the economy has digitalized. Over the last decade, the rise of expanded computational services has been accompanied by increased demand for associated cloud computing infrastructure. The data center industry's improving operational efficiency during this period initially held U.S. computing related energy use flat while servicing greater demand. The expansion of data center services into areas that require new types of hardware, such as artificial intelligence and cryptocurrency, is projected to break this trend, contributing to growth in American electricity consumption. So basically what they were saying is because of cloud, and therefore there are more companies using cloud and not necessarily building out more of their own data centers. Because enterprises were using cloud actually may have helped stabilize the electricity use, because you're mainly looking at who? Google, AWS, Microsoft Azure, and let's say Oracle, right? And so because of that, between those four, maybe IBM, they were able to have some increase, but still a level of a stable uses of energy. But now, because of cryptocurrency and because of AI and the GPUs, I'm sure they'll get into all that. That now has caused a shift and a more steeper curve as years or as time, is going forward. The expansion of data center services into areas that require new types of hardware, such as artificial intelligence and cryptocurrency, is projected to break this trend, contributing to growth in American electricity consumption. The exact magnitude of this growth remains a subject of debate due to the heterogeneity of estimation methodologies. These methodologies can be broadly categorized into three main approaches: bottom-up, top-down, and extrapolation. Analyzing these approaches will shed light on the strength and limitations of each for accurate data center energy use estimation, which is a good point. We really do want to look at as well, how are you guys doing these estimates? What information are you using? What's your methodology? And so that's why I think that this is a really good report, because we get to see exactly how this was done, and they're a third party. They're not. Anyway, continuing on. Bottom-up modeling delves deeply into the specificity of a data center. Using this method requires the meticulous gathering of data on individual components, such as the power draw of servers and a facility's overall efficiency. This information is then combined with estimates of equipment shipments and the number of servers already deployed to calculate total energy consumption. This method provides insights into individual components of data centers and their energy use, allowing for more granular analysis. While this approach approximates a physical model of the data center, bottom-up modeling has limitations. It is heavily reliant on the accuracy of the data regarding installed base, equipment sales, and shipments, as well as accurate predictions of technological changes. Bottom-up approaches necessarily require knowledge of the underlying installed equipment base. While existing contracts for future sales mean near-term shipment forecasts are reasonably reliable, bottom-up methods cannot estimate at the same level of accuracy once they become projections, owing to variations in equipment characteristics and operation, and require periodic updates to reflect such changes in their foundational data. Now, top-down modeling takes a broader view and leverages existing data from governments or industry organizations. This approach analyzes regional or national energy consumption totals, often derived from surveys and statistics. Aggregated estimates of service or product demand are then used to derive the required physical infrastructure to supply that demand. I think I might still like bottom up. In a review of 46 studies on data center energy estimation, Myton and Ashton found this method to be less common, with only one example of an exclusively top-down approach found in their analysis. So that was top-down. The relative ease and low cost of implementation are clear advantages of a top-down model, as illustrated by an example in Malmodin back in 2014. They utilize site-level energy measurements from various locations in Sweden, including 7 large data telecom centers comprising measured services, including 7 large data telecom centers comprising measured service demand from 15 offices, 58 stores, and approximately 11,000 fixed and mobile sites. This approach was paired with bottom-up equipment statistics to extrapolate a global estimate. This approach allows for the use of defined values, including the total measured network data volumes and total energy consumption values from electricity meters, which allows for accuracy, but only at a very high level of aggregation. Additionally, this approach encounters difficulties in understanding the impact of technology change compared to bottom-up approaches due to a limited breakdown of data center components that make up the overall estimate. Functionally top-down approaches interpolate the hardware stack based on service energy use. The last approach, extrapolation, builds on existing estimates, either bottom-up or top-down, to forecast future energy use. Extrapolation begins with a base value of data center energy use that is then extrapolated either using a projected annual growth rate or the basis of a service demand indicator when normalized to a unit of service such as IT traffic. This method projects future energy consumption based on energy intensity per unit of transmitted data by developing assumptions about overall market growth and energy efficiency improvements for future projects. While extrapolation methods are simpler and rely on less data than other methods, they rely heavily on the accuracy of the bottom-up or top-down models used, as well as assumptions about future market trends. These extrapolative studies are highly sensitive to errors in their input analysis, as extrapolation of most of those errors functionally compounds them. While they offer a useful benchmark for future demand, these methods must be used judiciously. A summary of the 3 main approaches to modeling data center use can be seen here. So I think obviously from what it said, this one is more accurate, the bottom up. The equipment specifications, they look at server power draw, data center infrastructure characteristics, like the power usage effectiveness, install base, etc. And they look, anyway, so this is something that you can kind of go through that table and go from there. Bottom-up models have historically shown more modest growth in data center energy use. In a 2007 report to Congress, the U.S. data center sector was estimated to have consumed about 61 billion kilowatt hours in 2006, equivalent to 1.5% of the total U.S. electricity consumption, for a total electricity cost of about 4.5 billion. In a follow-up report, the data centers sector was estimated to have consumed about 70 billion kilowatt hours in 2014, equivalent to 1.8% of total U.S. electricity consumption. This estimated level of electricity consumption is comparable to the amount of electricity consumed by approximately 6.7 million average U.S. households. While these estimates paint a picture of a gradual rise in data center energy use, other projections suggest a much more dramatic scenario. According to Reuters, 9 of the 10 largest U.S. electric utilities said data centers would be the main source of customer energy demand growth, stemming from technologies like generative AI, The electric utility Southern Company projects data centers will increase its electricity sales by 6% each year from 2025 to 2028, up from its prior predicted growth rate of 1 to 2%. Financial and industry analytic firms share similar findings. Boston Consulting Group estimate that data center energy use could triple from 2.5% of U.S. electricity consumption to 7.5% by 2030. Companies like Georgia Power, a subsidiary of Southern Company, have drastically increased their near-term load growth predictions based on growth from data centers. However, data center operators and federal agencies are seeking greater visibility into the company's heavily redacted resource planning filings, criticizing the utility's approach to load forecasting. Microsoft challenged Georgia Power's modeling methods, highlighting concerns that the model is undervaluing renewable energy while overestimating data center load for projects that have not yet selected Georgia Power as their provider. Utilities consistently emphasize data centers and specifically AI as the drivers of projected increases in electricity demand. 7 of 8 utility forecasts highlighted AI as a key driver of demand growth. Strategic consulting and financial analytics firms consistently predict expanded demand. It is noteworthy that in parallel with the predicted increase in AI-related computational demand, specialized microelectronics industry analysts have made more reserved estimates of short and medium-term load growth due to greater emphasis on manufacturing. Industry analytics firm SemiAnalysis projected AI would account for 4.5% of 2030 electricity use in its base case estimate. Institutions specializing in projecting energy use, or IT Power specifically, have also updated previous analysis to incorporate AI investment. Plots of both historical academic estimates and associated projections of data center energy use in the United States and globally can be seen in figure 1.1 and 1.2. So we'll look at that in a minute. We should not dismiss these projections out of hand, as the most extreme cases would constitute a significant stress on electrical infrastructure. Many underlying models on which financial analytics firms build these projections are proprietary or methodologically opaque. Basically, it's hard for them to really get the full transparency into how they got their data. Others are often extrapolations from utility load growth forecasts based on market research demand projections. While not meaningless, historical utility demand forecasts consistently overestimate both peak and average demand. Rigorous models of data center energy use are needed to adequately calibrate both future investment and public concern. So here's figure 1, academic and industry historical estimates of US data center energy use. This is 2020 here. This is 100 terawatts. And you can see here we are in 2025. They estimated about 200 terawatt hours. We were right around there because 2023 was 176 terawatt hours. And then this is their estimates going up. So And these are the different studies that were done and what they see. Bottom line, as you can tell here, from 2020, it's just going straight up. Whether straight up this way, it's going up. The demand is huge. This is 1.2 academic industrial estimates. All right. The Energy Act of 2020, U.S. Congress 2020, calls for the Department of Energy to make available to the public an update to the United States Data Center Energy Usage Report from Berkeley. That's the one we read before, which estimates historical data center electricity consumption back in 2000, hereafter referred to as the 2016 report. This analysis is designed to meet this Congress request to update the 2016 report and builds on the bottom-up technology-based modeling approach developed by Kumi, Massanet, and co-authors, etc., etc., etc. Bottom-up methods are recognized for their accuracy and robustness, stemming from their reliance on meticulous data collection regarding the IT equipment inventory within data centers. While limitations exist in using this approach, top-down estimates instead interpolate backwards from service demand, which has become increasingly uncoupled from electricity use in the IT sector. This study seeks only to estimate the direct energy use by data centers, not any underlying economic factors or transitions that may substantially change the underlying environment and technological basis. The remainder of the report is organized as follows. Section 2 describes the methodology employed in the study. Section 3 describes the categories and subcategories of IT equipment modeled in the study, including the power consumption estimates for various equipment types, how those estimates are evolving over time, and the calculation and results for the installed base of IT equipment. Section 4 then describes the different data center types considered in the study, how IT equipment is allocated across those space types, and the modeling of non-IT power and water demands, namely from the cooling systems, to estimate site power usage effectiveness, or PUE, and water usage effectiveness, or WUE. Section 5 then presents the resulting estimates for total electricity consumption, as well as the emissions and water footprints, considering the source energy of regional electricity grids. Section 6 provides a separate analysis of cryptocurrency. Section 7 summarizes findings, highlights limitations, and provides suggestions for future research. I really want to read this methodology overview, but I'm not going to do it now. I'm going to stop now. And what I'll do is, I think I'll do a separate video just on the methodology overview so that I can break up this, so that if someone in the future does want to read this through with me or read along as this is, that it's not so huge of a time block. Anyway, for those who have listened or those who have taken some time to read along or with me, I appreciate it. And that's it. It's 10 after 1 a.m. here in the garage, kind of just reading through this. So anyway, great article, and I hope you guys get your hands on it as well, so that you can really gather the information, which I think is good information to know as you are in the data center space or AI infrastructure space. So network engineers, architects, etc. Energy is a big deal. And so this is a good place to start, or it's a good place to add to your reading library when it comes to energy usage within AI infrastructure. All right. I'm Vernon Neal Reed, and this is AI Infrastructure Media. Have a wonderful night.